For this lesson, we'll be going over the fundamentals of transformers. Now, transformers typically have four purposes. We have a step-up transformer, which increase voltage, decrease current. Step-down transformer, decrease voltage, increase current. We have isolation transformers, which create a demilitarized zone or an isolation between one part of the circuit from the other. And they have impedance matching transformers, which entails pretty much matching the input impedance and output impedance to maximize power transfer. When performing transformer calculations, you need to know if you're doing real transformer calculations or ideal. Ideal transformers are lossless devices. They're considered to be completely theoretical. In other words, power in will equal power out. Real-world transformers are not lossless devices. They're considered to be more practical and used for real-world applications. The reason they're not lossless devices is because they create heat due to power loss. Now, in most of your textbooks and in this lesson, we're going to be dealing with the ideal transformers. Typical transformers consist of two sets of windings, the primary side and the secondary side. And based on the amount of turns in those windings, will also tell you how this transformer will impact the circuit. The amount of turns is referred to as the turns ratio. And this actually translates to how many turns from the primary side to the secondary side. So in other words, if you have a 2-to-1 ratio, there's twice as many turns on the primary side than the secondary side. Now with these turns, you also have the dot rule, and that determines the current direction between the source and the load. The dot is based on the winding direction. Now we can jump right into the fun part. When performing your circuit calculations, it would be ideal to simplify down your circuit to mimic the schematic that's shown here. Once you simplify it down to this simple schematic, you can use the equations above to provide an output based on the variables provided. On the earlier slide, we talked about impedance matching as one of the key purposes for transformers. It's important because it's used for maximum power transfer. The objective is, by matching the impedance, you can extract as much power as possible from the source to the load and minimize loss. Now I have a schematic here that provides a red side and a blue side. The red side is your primary, the blue side is your secondary. When performing your calculations, if you took a meter or you did your calculations visualized by the red side, it's going to see the load as you see in the bottom left where it says reflecting from secondary to the primary. And if you're doing your calculations or performing your readings based on the secondary side, then you're going to have the blue, which is reflecting primary to secondary. And then we also have the calculations for power loss, which we'll go over more in some of our example problems. All right, let's jump right into our first example, and this one's going to be an easy one. For this one, we want to determine the turns ratio to match the impedance of the following configuration. This is a very simple schematic here. We have a radio going into an audio amplifier, and the audio amplifier is going to a transformer, and the transformer has a load of two output speakers rated at 50 watts at 8 ohms each. So this one can be considered a real-world application. Just like all of our examples, let's start with what we know and what we don't know. What we want to know is our turns ratio, and that is alpha. So we want to know what A is. Okay? Now here's what we know. The audio amplifier has an input impedance of 16 ohms. So it's providing 16 ohm impedance to the transformer. So that 16 ohms can be considered Z of 1 because that's on the primary side. Now here's where the tricky part comes in. On the secondary side, on our load, we have two speakers with an 8 ohm impedance each. Now that doesn't mean the load is 8 ohms because they're in parallel. We'd have to actually turn this into a single component or single impedance. So since they're in parallel, we'll go ahead and revert back to our fundamentals. Z of 2 equals, and we'll do the first speaker, which is 1 over 8 ohms, plus 1 over 8 ohms for the second speaker. And that's going to give you 1 over your answer. And if you plug and chug that in a calculator, it's going to be 1 over 0.25. And then if we plug and chug that in a calculator, it's going to give us an answer of 4 ohms. So Z of 2 is going to equal 4 ohms. Okay, so far so good. Now we're looking for turns ratio. If you look to the equations to the right, the one we can use that would be the easiest would be this guy right here. So we're going to say turns ratio squared equals Z of 1. Tell you what, I'll just write out right here. and over Z of 2. All right, and we know Z of 1 is 16 ohms over Z of 2, which is 4 ohms. And I don't think we need a calculator for this one. 16 over 4 equals 4. All right. Now, the one thing that people usually stop on and they forget to finish up is the square. We need to get rid of the square. So A of 2, A square in this case, equals 4. So we square root both sides, and that's going to give us an answer of A equals 2. So for this problem, we have a turns ratio of 2 to 1. So you have 2 times as many turns to 1 to have a matching impedance for both sides. All right, so this one was pretty easy. This is a good one to get your feet wet on. Let's go to the next example. All right, for our second example, we have something a little bit more exotic. A building is connected to the load side of the following circuit. So we have a building right over here, and it has a voltage and current demand of 240 volts at 200 amps, similar to our source. Between the load and the source, there is 200 feet of 4-gauge cable, and that comes out to be 0.065 ohms per 1,000 feet. And we want to determine the power efficiency of the following configuration. So we want to determine power efficiency. So we're looking for efficiency. I'll put a question mark right there. Now, what do we know? We know our source is 240 volts at 200 amps. We have a 1 to 20 ratio going through a long cable, and then it drops back down to a 20 to 1 ratio. So the first thing I want to do, I want to determine how much resistance is in this cable. So I have 2,000 feet, and we know for every 1,000 feet, it's 0.065 ohms. So we'll say our resistance for the cable is 2,000 feet times 0.065 ohms per 1,000 feet. And as usual, excuse my handwriting, you know it's terrible. So if we do 2,000 times 0.065, it's going to come out to be 130. I'll tell you what, I want to make up some random unit, and that's over 1,000 feet. And then if you keep going, and if you do 130 foot ohms divided by 1,000, it's going to come out to be 0.13 ohms. And the reason being is feet cancel out, so all you have left is your resistance. So this cable is providing a resistance of 0.13 ohms. So the next thing we want to do is we want to determine how much loss is within this cable. We want to determine power loss, which is this guy right here. All right, now this is where it kind of gets a little bit interesting. So I want to determine the current going down this cable. Because if I can determine the current, I can determine how much power it's actually, or how much loss we have within that cable, because we have resistance, and with current resistance, current square times resistance will give you power. And I'll show you how we can do that. So we have 240 volts here at 200 amps. And that is a step-up transformer. It's going from 1 to 20, which means it's upping the voltage 20 times, which also means it's dropping your current by 20. All right, so this one's not very difficult. We're going to refer back to our first equation right here. Turns ratio equals V1 over V2. So I'm going to write it out. So we have our turns ratio equals V1 over V2. All right, our turns ratio is 1 over 20. So we're going to have 1 over 20 equals V1, 240 volts, over V2. Now what I can do is I can go ahead and swap these two around. I can put my 1 over 20 on my denominator, and I put my V2 on the other side of the equal sign. So it's going to look something like this. V2 equals 240 volts over 1 over 20. Now if you put 1 over 20 in your calculator, it's going to give you, okay, we'll do it one more time. V2 equals 240 volts over 0.05. So if you plug and chug that in your calculator, your V2 is going to give you 4,800 volts. It's a lot of volts. So we'll put that right there, 4,800 volts, if you could see that. But we want to determine our current. Well, that's actually using the same equation, just in a different way. I'll tell you what, I want to clean this up real quick. So I'm going to say my turns ratio equals I2 over I1. So turns ratio, same thing. I'll tell you what, 1 over 20 equals, I don't know I2, but I want to find out, but I know I1, 200 amps. And if I multiply, put that right there, if I multiply 200 times 1 over 20, it's going to look like this. 200 over 20 equals I2, which means we're going to have a current of 10 amps. And tell you what, let me put my units right here. That way we know which one's which. So we have 10 amps on I2 now. Instead of from 200 amps, we went from 10 amps. That's a great thing. Now we'll show you why. So current is 10 amps. So now let's determine our power loss going through this cable. The way you determine power loss, and that's P loss, is going to equal, and this is a common power equation, I squared times R. Well, we have our current, and it's going to be 10 amps times our resistance, which is 0.13 ohms. 0.13 ohms. And make sure I didn't forget the square there. Plug and chug that in your calculator. It's going to give you an answer of 13 watts. All right. So right away, we have a power loss of 13 watts. Tell you what, let me go ahead and start writing these up here. That way I can erase more on the screen. The power loss equals 13W. All right, so I'm going to erase this to make a little bit more room. Now looking to the right, I think we have enough information to determine our efficiency because I have power loss now, and then I have P2 because my P2 was my demand, which was 240 volts at 200 amps. So our efficiency is going to equal P2 over P2 plus your power loss, and that's going to equal your efficiency. And then if you want the percentage, you multiply it by 100. But we'll first go ahead and determine the efficiency. So P2 is 240 volts times 200 amps. And then we'll do the same thing down here. Tell you what, do it in parentheses. 240 volts times 200 amps. And then plus your power loss, which we determined was 13 watts. And 240 volts times 200 amps is going to give us an answer of 48,000 watts. And that's going to be over 48,000 watts plus 13 watts. And that's an easy plug and chug in the calculator. Your efficiency is going to go to a whopping 0.9997, and we'll stop there. So that's pretty good efficiency, 99.9%. Because when you multiply that by 100, it's going to give you efficiency of 99.97%. That's a pretty good percent. Now you're probably thinking, why do we use a step-up transformer and then a step-down transformer? We're going to show you why. So with this answer, we already determined it's 99.97%. So we'll write it right there just so I can show you why. Let's say we go and omit these transformers completely. We leave the cable and we don't even have a step-up and a step-down transformer. We're going to have 240 volts at 200 amps go through this cable. So you know right there your power loss is going to equal I square times R. Well, we know our R and we know our current. So that's going to equal 200 amps square times your resistance, which is 0.13 ohms. That's going to be a pretty big number. If you plug and chug that in your calculator, it's going to give you an answer of 5,200 watts. So you have a power loss of over 5,000 watts by not using a step-up transformer because you want to lower your current. By keeping the current high, you have a high power loss. Let's go ahead and finish out the equation. So we know our efficiency is going to be P2, which is, we already determined earlier, was 48,000 over 48,000 plus, now you have over 5,200 watts of loss. And if you plug and chug that in your calculator, it's going to give you 0.90, and we'll say 23. We'll stop there. So that's a pretty bad efficiency. You went from 99.97% to 90.2%. That is not a good efficiency. So that is the reason they have a step up and a step down transformer for this particular circuit. And we'll do, I just want to finish this out, that way you can see how I got that percentage. So that's without a transformer. Without. I think that's enough to get your feet wet for this one. Let's do our last example problem. All right, for our last example, this one's not very difficult, but I want to go over it with you. That way you get an idea of how we're going to manipulate the circuit based on which point of view you're looking at. All right, so for this one, we want to determine V1 and current 1, which is both primary side voltage and current for the following circuit. So we want to know this guy right here, and we want to know this guy. Now, what do we know? Well, we know R1, and I'll put it over here, equals 150 ohms. So far, so good. We know R2 equals 15 ohms. We know our turns ratio is 5 to 1, which means A equals 5. It's pretty good so far. And then we have our source, and I'll put it right here. Your source is 60 sine. All right, so we have a little bit to work with here. Now this one, you're going to refer back to the PowerPoint on the maximum power transfer slide. There's a particular schematic we're going to use to solve this problem. So we're going to look at this circuit from this point of view, which means we're going to be referring to that PowerPoint and using that circuit setup. So let's look at it. They have a source, which is in this case 60 sine. They have R1, and then you have your transformer seeing a resistance of R2 times your primary turns ratio over your secondary turn ratio, and that's square. And that's going to mimic something that looks just like that. So that equation right there is going to go right on the primary side of that transformer. If we have our circuit set up here, we're going to have our source, which is 60 sine, and that's going to go to R1, which is 150 ohms. And then, if you're looking at this and you're trying to do your measurements, and the transformer is going to see a resistance of your load resistor times and N1 over N2, which is your primary turns and your secondary turns, that is your turns ratio. That's A, and that's going to be square. And that's what you're going to see from the primary side. So that's how you're going to determine your current. And once you have your current, you can determine your voltage. Say we'll make that a 1, since I typoed that one. Well, we have the load side resistance, and we have our turns ratio. So which means, let's say I will put it right here, we'll say R2 is 15 ohms times your turns ratio, 5, and we're going to square that. So that's going to give us 15 times 25, and that's going to give us a resistance of 375 ohms. I'll tell you what, put my resistance there. So this one is seeing 375 ohms, which means we can go ahead and determine our current for this circuit. So if you add R1 plus what your transformer is seeing, which is 375 ohms, that's going to give your total resistance. So in a sense, your RT is going to equal 150 ohms plus 375 ohms. And that's going to give us an answer of 525 ohms. So far, so good. And how do you find current? Well, I equals V over R. An old classic. So which means our voltage, 60 sine over 525 ohms. And that's an easy plug and chug in your calculator. It's going to give us 0.11, and we'll stop at 4 sine. And that's going to be amps. So that's how much current is going through that transformer right there. It's 0.114 amps. Okay, and now we need to still find V1. Well, that one's just as easy. We have our resistance right here, and we have our current. So, same concept, V equals I times R. So I have my current, 0.114 sine, times my resistance, which is 375 ohms. And that's going to give us a final answer of, let's see if I can fit it down here, 42.75. And that's going to be, again, sine volts. So this one's pretty easy to do as long as you understand how you're doing your calculations based on what side you're looking at. Because I was doing my calculations as if I was looking or seeing the circuit from the primary side. I can also figure out the same concept by doing it from the secondary side too. I just have to use the second half of that circuit that we had in the PowerPoint. If you have any comments, questions, concerns, don't hesitate to ask, and I hope you all have a good day.